Welcome to today's webinar, Development of an Aero-Servo-Elastic Module for the Next Generation of Horizontal Axis Wind Turbines, brought to you by CONVERGE Science. Thank you for joining us today for the second installment of the 2024 CONVERGE webinar series. My name is Mattias Sulis and I am part of the business development team at CONVERGE Science. I will be your host for today's event. I'm glad I can be here with you today and learn from the winner of the 2023 CONVERGE academic competition, Leonardo Pagamonci, about how it is possible to investigate the aeroelasticity of wind turbine using CONVERGE. CONVERGE Science is a rapidly growing computational fluid dynamics software company. Our flagship product, CONVERGE, is an industry-leading CFD solver used around the globe to simulate fluid flows in complex systems. CONVERGE features truly autonomous meshing, which eliminates all user meshing time and helps provide fast, accurate results for our clients. Now it is time to introduce our speaker for today's event, Leonardo Pagamonci. Leonardo received a bachelor's degree in mechanical engineering in 2017 and a master's degree in mechanical engineering in 2020, with the thesis on the development of an actuator line code for the simulation of vertical axis wind turbines. He worked for a year as an HVAC engineer for an engineering firm, then began his Ph.D. studies in 2021 in industrial engineering at the University of Florence. Without any further delay, I will now pass the ball to Leonardo. Thank you all.
Thank you, Mattia. I'm Leonardo Pagamonci. I'm from the University of Florence, and my PhD project involves the development of an Aero-Servo-Elastic module for the next generation of horizontal axis wind turbines. Nowadays, the wind energy matures, and with that, wind turbines are increasing in size, with larger rotors with more deformable blades. Moreover, wind turbines are clustered in wind farms with many interaction between the rotor and the wakes of the upstream rotors with the downstream one. And in this perspective, CFD can help to solve the many challenges arising from both the analysis of the single rotor, of the aeroelastic response of the single rotor, and an aeroelastic response of the many rotors that are involved in a wind farm installation. First of all, let's have an introduction of aeroelasticity. With wind turbine blades that are flexible and slender structures, they bend and twist during the operation, with changing in operating conditions. And this important mutual interaction between aerodynamics and the elastic response of the blade can cause important changing in their performance, and it's important to be accounted in during the design of these blades. And they are also unavoidable in a flexible blade design, and so to take them into consideration is key from the performance prediction, and sometimes it may be also desirable to tailor this effect to our advantage. And high-fidelity models can help us to understand these effects. Regarding the wind farm installations, when analyzing many rotors, many turbines operating in a wind farm, their wakes interact one with each other. But how do they impact on the loading of the structure, and how can we account them in the rotor design? And once again, CFD can give a very important contribution in these terms by solving this turbine-to-turbine interaction. But what is the main issue when we talk about CFD analysis of wind turbines? Basically speaking, there is a very huge interval of landscapes involving wind energy, wind turbines, passing from the very small landscapes of the boundary layer and going to the very large landscapes in the order of kilometers or tens of kilometers while talking of a wind park. In this sense, full CFD analysis would require, even for the largest clusters, weeks, if not months of calculations. And to give an help in this sense, many hybrid methods have been developed to blend a modeled analysis of the smaller scale with the solved approach for the larger scale. Hybrid methods are characterized by three basic components. The flow field, which is solved by means of CFD, either RANs or less LES simulations. And on the other hand, a low-order modeling of the rotor, usually based on input airfoil or turbine data. And in the halfway of this analysis, we usually have an interface between these two approaches for the exchange of information between the flow field data solved by CFD and the modeled forces and modeled response of the rotor by the lower order model. One of the most developed and widely adopted tools and model among the hybrid methods developed in literature is the Actuator Line Model. With this method, we replace the geometrical presence, the geometrical shape of the blade with the dynamical equivalent volume forces that are exerted by the blade itself. The actuator line is discretized in multiple actuator points. For each one of them, 2D sections are defined. And with tabulated data, we have the lift and drag coefficients of these sections. And once we have from the flow field solved by the CFD the inflow characteristics like the velocity and the angle of attack, they are used as an input together with the tabulated airfoil data to calculate the forces. But once these forces are calculated, they are calculated in a lump parameter approach. And so to avoid discontinuities and instability of the solver, they need to be spread into the domain by means of the so-called regularization kernel. Once the forces are inserted into the flow field, these momentum sources are used to solve the flow field by the CFD itself. And together with aerodynamics, another important element that can be calculated by this approach is also the displacement of the actuator point from the equilibrium position of the blade in the rigid configuration. So it means that also the elastic response of the blade can be calculated. And it is in this background that my PhD project takes place, and it brought to the development of CALMA, that stands for CONVERGE Actuator Line Model for Aeroelasticity. With this module, the widely adopted and widely validated engineering tool OpenFAST has been coupled to CONVERGE, and with this coupling, we enable Aero-Servo-Elastic CFD simulations of single or multiple rotor configurations of horizontal axis wind turbines. And in this framework, OpenFAST is called to solve the aerodynamics, basically with a model that is based on a blade element theory approach. The structural solver is one based on the model approach and solves the deformation of the blade in the flapwise and bedwise directions, so torsions are not included. And the turbine control is done by means of a dedicated module that is available inside this framework and resembles all the control strategies and control logics that are usually available inside a wind turbine installment. In this framework, CONVERGE is called to give the inflow data as an input to this framework. And once the forces are calculated, to be inserted again inside the CFD solver in order to calculate the final effect like induction and the final deflection that can be noticed inside the flow field. With a deeper insight of this coupling, basically, so we have CONVERGE that solves the flow field, gives the input to OpenFAST, solves the aerodynamics, the aeroelasticity, and all of that with the control strategies active and available on demand. And once loads and deformations are calculated, they are given back again as an output to the solver. And here, in this GIF, we can see what is the final effect of such a coupling. So here we can see the flow field that is solved by CONVERGE, and this flow field is sampled, and the flow in front of the rotor, the flow field data in front of the rotor are given to OpenFAST. And what we see here is the final effect, the final output. So with an ISO surface of action forces, we can actually see that the position of the blade and the position of the tower, also available, can be inserted inside the domain together with the volume forces that are calculated by the engineering tool. We mentioned the control strategies, and here we can see an example. Usually small turbines, but especially larger rotors, can be controlled with this pitch to feather maneuver. When a rotor needs to be stopped, the pitch angle of the blades can be regulated and controlled to move the blades to a feather, so-called feather position, and the rotor speed can be controlled, decreased, and even stopped by this maneuver. Another example of the control strategies that are available in this coupling is the yaw maneuver. This is another widely adopted control strategy for small rotors, but also in large rotor wind farms, and we will see an example later. After that, this tool has been widely calibrated and validated. It has been adopted for the main purpose of aeroelasticity. That means how it impacts to the wind turbine at scaling. In this sense, another important element in analysis of these large rotors is the reproduction of realistic and turbulent and sheared wind inflow conditions. And in this sense, this model has been included inside the CONVERGE framework. And turbine stands for turbulent random boundary U-velocity inlet Norban distribution. And with this function, random velocity perturbations calculated with a user-defined timing and an Gaussian probability distribution can be used to include these macro turbulence effects inside the run simulation. And all these, together with other already available features inside the CONVERGE framework, we are able to calculate sheared and turbulent inflow conditions in front of the rotors. In this case, the analysis of the effects of the wind turbine upscaling has been done for starting from the NRL 5 MW, that is a turbine that has almost 20 years, towards the IEA 15 MW to see what is the effect of such an upscaling. We talk about almost double of the size to the final aeroelastic response of this turbine. As expected, looking at the mean values of blade tip displacements, we can already notice changing and an important increase of the final values of this deformation in the flapwise direction. And most important, by including also frequency variations of the blade response given by the variation of the wind conditions during the revolution, we can see both in the time series domain and in the frequency response of the blades that with the upsizing of the rotors, also higher values of loads, higher values of frequency loadings can be noticed on these rotors. Another important outcome can be inspected if looking at the structural velocity and on the structural response of the blades in terms of velocity and the direction of the deformation during the revolution. If we look at these graphs that indicate the structural velocity of the blades with the positive values that are in the same direction of the wind, and with the negative values that are in the opposite direction of the wind, and with the 0-degree angle that means the blade pointing up, we can see that in the upper region of the rotor, the final apparent wind reaching the blade section is decreased by the effect of the structural velocity, while on the lower part of the rotor, we can notice an increase of the apparent velocity of the wind. And so by the end, a final increase of the relative velocity of the wind. This effect basically filters the incoming variable wind profile during the revolution. And the final effect of such a result can be noticed if looking at frequency response of aerodynamic quantities like torque. If we look at the 5 megawatts, the inclusion of flexible effects wasn't so meaningful in terms of final frequency response. While if looking for the 15 megawatts, this caused a very huge variation in terms of the final frequency response in terms of torque during the revolution at 1 times the revolution frequency. And this is one of the examples of the important outcomes that can be given by including the aeroelastic effect and in analyzing the aeroelasticity in the blade. So to summarize, here with this tool, we are included the shear flow and the macro turbulence in terms of incoming inflow conditions in order to generate turbulent structures, realistic turbulent structures in an atmospheric boundary layer approaching the rotor. And also with the inclusion of OpenFAST, it's available the aerodynamic analysis, the elastic analysis, the structural analysis of the blade, and also the inclusion of the control strategies. And all these can enable analysis like the ones shown here. For example, it's possible to control the upstream turbine in a wind farm arrangement. And in this tandem configuration, by controlling the yaw angle of the first turbine, it is possible to cause a wake steering that can cause different effects in terms of aeroelastic response to the second row of turbines. And this shows one of the many potentialities of including Aero-Servo-Elastic analysis of wind turbines, horizontal axis wind turbines. And so we have seen the importance of the inclusion of Aero-Servo-Elastic analysis for the simulation of horizontal axis wind turbines. But what's next? We for sure know that the external turbulent wind conditions severely affect the elastic response of the blade. And so realistic and accurate inflow conditions increase the final accuracy of these tools. And in this sense, many solutions can be proposed. For example, the LES simulations by the use of precursor and successor technique, or the inclusion of the turbulence inside the flow field by generating it in front of the rotor with an approach that, for example, comes from the man-box theory. This on the side of the realistic inflow condition. In terms of structural solvers, many improvements can be included. For example, the inclusion of the torsion. And in this sense, the implementation of the module like beamdyne can work in this sense by passing from a modal approach as done in Elastodyne to a 1D beam approach as done in beamdyne. And so with this, I conclude my webinar, and I thank you for the attention and hope you enjoyed this webinar.